everybody. Welcome back to Mathematical Statistics. We have been talking about confidence intervals and my long-held desire to not use normal distributions anymore when I don't have to and look at parameters other than the mean mu. And we are there. We had just started an example, so I am going to jump right into it. At the end last time, we were talking about a random sample or a bunch of IID random variables from the exponential distribution with rate lambda. And we wanted to find a 100 times 1 minus alpha % confidence interval for lambda. So no more normal distribution. I'm going to say find or derive. That sounds fancier, doesn't it? A 100 times 1 minus alpha % confidence interval for the rate parameter lambda. Now, normally I'd put a period right there. That's the end of the problem statement. But because we're just getting started, I do want to help you out to get going with each problem. So I'm going to give you a statistic to start with for now. So I'm going to say based on the minimum value in the sample, which is strange. I think the minimum, which is going to keep pushing down towards zero every time you get a sample and you make it bigger and bigger, the minimum is going to get smaller and smaller, is not a good estimator or statistic to work with when wanting information about lambda. But it's easy to work with because we know its distribution. So it's just a first example. And in my second example, we'll look at the same setup, but a different statistic. Let's go. Step one is always to choose a statistic. Obviously, this has been done, but I'm including the step for completeness. We're going to use the minimum value in the sample. Step two is to find, this is the last time I'm going to write this out long because we have a word for it, but find a function of the statistic and the parameter we're trying to get at, in this case lambda, whose distribution is known to us. And this and part is kind of included in the distribution is known, but to be clear, is unknown parameter free. It's probably the least clear thing you've seen today. So what does that mean? The pivotal quantity, we need to know its distribution. Is it a normal? Is it an exponential? Is it Pareto? Is it something unnamed, but we have the PDF? And we want to make sure it doesn't depend on any unknown parameters. So in this case, we want to find a function of lambda and the minimum whose distribution does not depend on lambda and whose distribution we know. To do this, I gave you a hint at the end last time and sent you off to go kind of figure this out. Outside of the context of the problem, I'm just going to get a whole new space here and come back to this. I'm sorry, that really stinks for you trying to take notes. But I had you look at a random variable x that is exponential with rate lambda. This is its whole own thing. I'm not using any notation from the problem. And I wanted you to look at the distribution of a new random variable y defined to be c times x for a positive constant c. Did you do it? One way to do this is think of it as a G inverse problem where y equals g of x is c times x, and then you can find the PDF for y. And that should be pretty smooth. But I'm going to use a different result, one that we've seen a few times already, several times. And that is that a constant times a gamma random variable is another gamma, where the constant goes under the second parameter, and the fact that an exponential is a special case of a gamma. So if none of this makes sense to you, just go back to this way and just go for it. But as another aside on my aside, so I'm reusing this letter name. This is like a separate thing over here. If x has a gamma alpha beta distribution, then the PDF is 1 over gamma of alpha, beta to the alpha, x to the alpha minus 1, e to the minus beta x on 0 to infinity. And so it's easy to see that if you plug in alpha equals 1, this part is going to go away. And we will get 1 over gamma of 1, beta to the 1, x to the 0, which is gone, e to the minus beta x, times an indicator from 0 to infinity. We did show that gamma of 1 equals 1, but even if we didn't, I would look at this right now and I'd say, this looks like an exponential PDF with rate beta instead of lambda. And that means that this term must be equal to 1, because if you have 3 times an exponential PDF, it's going to integrate to 3, because you can pull the 3 out of the integral and the rest of the PDF integrates to 1. So whether or not you remember things about the gamma constant, we know this has to be 1 just because we see a PDF in here. I guess I didn't write down what I was doing for this line, but I was looking at the gamma 1 beta distribution, and that's how we got an exponential with rate beta. We also saw that, um, let me move this up. This is some poor planning here. We also saw that if x has this gamma distribution and c is a positive constant, starting with this, c times x has a gamma distribution with parameters alpha and beta over c. We've used that at least 4 times in examples in class. So I know we've seen it a lot. And using that and the fact that the exponential is a specific type of gamma can get us this distribution pretty quickly without having to do the G inverse stuff. Not that that's really terrible. So x, which is exponential with rate lambda, is actually also a gamma distribution with parameters 1 and lambda. And a constant times x is a constant times a gamma, which has the gamma distribution with parameters 1 and lambda over the constant. This constant does need to be positive. It's not to say you couldn't do the problem with a negative constant, but it wouldn't have a nice known name distribution. I mean, you can say it's like a gamma, but it's on the negative x's, but technically it's not a gamma distribution that way, or something with a name. We want to find a function of an exponential random variable and lambda whose distribution is known and unknown parameter free. For example, if we were working with this statistic, I'm still not back to the specific confidence interval problem, but if I had a random variable x that's exponential with rate lambda, and I wanted you to find a function of x that doesn't depend on lambda, you can see from here that all I need to do is multiply by lambda, because this second parameter will end up being lambda over lambda, which is 1. So no parameters left over. In other words, lambda times x here would be chi squared 1, 1, and that is the exponential distribution with rate 1. So let's go back to our confidence intervals. Step 1 was to choose a statistic, and we're using the minimum. Step 2 is to find this pivotal quantity. That's what this is called. And that's a function of the minimum and the parameter whose distribution is known to us and not depending on any unknown parameters. So recall that the minimum of exponentials is exponential with rate n lambda. That's why I chose this statistic to work with, not because it's going to give us a great confidence interval. We're going to get a confidence interval of a specified percentage, like 95%. But if you did it with a better statistic and also computed a 95% confidence interval, that one would probably be a shorter interval, which is better when you want to give someone an interval of plausible values for lambda. So in step 2, we want to find this pivotal quantity, and I would always start off by looking at the distribution of the statistic you're going to work with, and then think about how I can adjust it. If I multiply by lambda, I'm going to put a lambda under here, and then I'll have an exponential distribution with rate n. You could continue along with that, but I think it's going to be cleaner to get rid of the n as well. So note that n, this implies that n times lambda times the minimum is exponential with rate 1. That is nice and clean. Step 3 is to find appropriate critical values for this distribution. This is where you look at this distribution and look at its PDF and try to find 2 points on the x-axis that capture area 1 minus alpha in the middle. Because our pivotal quantity has an exponential rate 1 distribution, let's look at the exponential rate 1 PDF. When x is 0, it starts at 1 and then it drops down exponentially. We have a lot of options here to capture area 1 minus alpha. We can do it like we did with the normal distribution and put area 1 minus alpha between two numbers, putting area alpha over 2 up here and area alpha over 2 down here. But this distribution has a left endpoint, unlike the normal distribution. So we could also consider just finding a single value and going from 0 up to that single value, as long as it captures area 1 minus alpha here and then the remaining alpha here. As a third option, we could go from some value to infinity and try to get area 1 minus alpha here and alpha here. That is looking a little strange because we're trying to find a confidence interval and it will result in an infinitely long confidence interval, which would still be correct as long as no one's asking you for some kind of optimal interval. Something like this could actually result in an infinite confidence interval if, when you're solving for the unknown parameter in the middle of the inequality, which is part of step 4, you end up flipping something that has a 0 in the denominator. You could have a problem with a setup like this as well. For our normal example, we did this sort of thing, and you can do it here as well. But it is quote unquote easy to see that this scenario is going to give us the shortest interval because most of the area for this exponential is down here towards 0. So if I try, so I'm in this picture now, if I try to take this endpoint and move it up a little bit and grab a different left endpoint, because there is relatively little area here compared to what I just lost, I would end up having to move that right endpoint further to keep the area 1 minus alpha. We could also show with calculus that if you decide to go from any a to a plus b and you optimize, you look at the a formula for, you work out the confidence interval. You take the right endpoint minus the left, you work out the length of the confidence interval. It's going to be a function of A and B, and you can do calculus to figure out how to minimize that length. But again, for us, it's this one. And even if it's not clear to you, that's okay. Also, in this course, I don't think I'm ever going to ask at least the undergrads to optimize the length of a confidence interval. Maybe there'll be a grad problem where you guys have to find an optimal confidence interval. But as long as you find any confidence interval with the given confidence level, for the rest of you, it's going to be just fine. Let's go with the middle one just for fun. And yeah, for optimality. But even if we didn't know that, I'm just going with it. I need to find a number such that I capture area 1 minus alpha between 0 and that number. So far, we've used normal distributions and t-distributions, and we had to find these numbers in a table because we can't do the integrals in closed form, or a computer can bring up, Mathematica, MATLAB, or something like that, and do numerical integrals. For this problem, we can actually do it pretty easily algebraically. If you want the area for the exponential up to some question mark, that is the CDF. I need notation here. So let me use a W just because I don't want to mix it up with the X's in the problem. If W is exponential with rate 1, then the probability that W is less than or equal to the question mark needs to be 1 minus alpha. For the left side, if you know the CDF, just write it down. But if not, it's going to be the integral from 0 to question mark of that exponential rate 1 PDF. And when you do this integral, you're going to get 1 minus e to the negative question mark. And then on the right-hand side, you're going to have 1 minus alpha. So take care of those ones. You're going to end up with e to the minus question mark equals alpha. Take the natural log of both sides and move the negative over. You're going to end up with question mark equals negative log of alpha. So that's this number right here, such that together with 0 gives us area 1 minus alpha down here. Let me get rid of this mess from before. We've done it. We have a pair of critical values, 0 to the negative of log of alpha. By the way, you probably recall that the graph of log, it starts at negative infinity and then gets positive when x is 1. So when you plug in numbers between 0 and 1, it is negative. And alpha, being a probability that we're trying to capture, is between 0 and 1. So the log of alpha is negative. So it does make sense that this right endpoint has a negative in front of it, because overall this is positive. That's not a bad tip for all you do in here and your other classes. Just do some quick, you know, common sense, does this make sense or not, and persevere. We are at step 4. Here, we want to put the pivotal quantity between the critical values, and we'll have a system of inequalities. And we want to solve for the unknown parameter, in this case, lambda, in the middle, if you will. We're going to have two inequalities, and we want to get lambda stuck between two things that do not involve lambda. We know that 1 minus alpha is the probability that W, where I'm using the same setup, W is exponential with rate 1. We know we can get that area in many ways. One of them is putting it between 0 and the negative log of alpha. W is exponential with rate 1. And the other thing in this problem that's exponential with rate 1 is n lambda times the minimum. So now I've got these inequalities, and I could solve for lambda in the middle. I'm simply going to divide by the rest of it. N is a sample size, so it's not negative. These x sub 1 in parentheses is a minimum of exponentials, and they only take on non-negative values. And so this is not negative, and we're not dividing by any negatives. But watch out in general, when you divide here, you might end up flipping some inequalities. We won't. We'll end up with 0 divided by n times the minimum, which is 0, less than lambda, less than the negative log of alpha over n times the minimum. So A, 100 to conclude, times 1 minus alpha percent confidence interval for lambda for the exponential distribution and based on the minimum, I'm too lazy to write that all out, is 0 to negative log of alpha over n times the minimum. You go give that to the person with the data, and they've got a certain number of data points, so they know n, and they've got they can compute the minimum, and they probably have a desired alpha. They want a certain level of confidence, not feelings, in their interval. So these numbers are going to be known to the person working with the data. And I did say A, not V. There are many confidence intervals, maybe uncountably many confidence intervals you can make for lambda for the exponential. But even if we restrict ourselves to intervals based on the minimum, we have so many ways to put that area in. Let me just go back real quick to those options. We have more than 3 options. Well, as I kind of have here, these shifted options. So maybe we put area 1 minus alpha between two values and only put 1/3 of alpha to the left and 2/3 of alpha to the right. Something like that. There's so many different things we can do. But we have a confidence interval here, and it happens to be optimal in the sense of length. given you are looking at the minimum as your statistic. Overall, I don't think it's a good interval because the minimum does not have very much information about lambda at all. Let's go to a second example, which is basically the same example, but with a different statistic that I think should give us a much better result. We have x1 through xn, IID, exponential with rate lambda. And I want to find or derive a 100 times 1 minus alpha percent confidence interval for lambda based on a different statistic based on the sample mean x bar. I'm going to add something else to this problem that isn't going to maybe be well motivated until we hit it in the problem, but I'd rather put it in now than have to scroll back and write it. So you'll see why I'm writing this, but leave your confidence interval in terms of a chi-squared critical value. When we find our pivotal quantity and find the distribution, it's actually going to be much like the normal was, something we can't find exact algebraic answers for critical values. So we're going to have to do it numerically. Historically, statisticians carried around a few tables, probably 3 tables, a normal, the t-distribution, the chi-squared distribution, and something we haven't talked about at all yet called the f-distribution. But they had to cut it off somewhere. They didn't carry around tables for a beta distribution or anything like that. So I think it's a little bit lame that I keep giving these symbolic critical values, but you know what they represent. They're cutting off a certain area, and you could go get those numerically. For this problem, I want to give them symbolically in terms of the chi-square because you're going to grow to see this semester that the chi-square distribution is as, if not more important, as the normal distribution in statistics. There's going to be so many results that hinge on knowing things about the chi-square distribution. So I want to kind of steer us there and start thinking about more things in terms of the chi-square distribution. That's what we're doing here. Okay. Step 1 is to choose a statistic. Each time I write this, I'm getting briefer and briefer. But that has been done for us. We're going with X bar. I write out step 1 just for completeness here. Step 2 is to find a pivotal quantity. This is a function of that statistic and the parameter lambda, whose distribution is known to us, and unknown parameter free. What can we do with X bar to get it to a distribution that is not dependent on lambda? Let's first look at the distribution of X bar. You may recall that we've already seen that X bar for an exponential distribution has a gamma distribution, but I think what you're more likely to recall is at least that the sum of an exponential is gamma. So if you know the answer to this, go straight there, but I am going to rewrite this like this. And then this sum of n IID exponentials with rate lambda is gamma with parameters n and lambda. And when you multiply, this is like the c, by a positive constant, that constant ends up under the second parameter here. So we will get a gamma distribution with parameters n and n lambda, which comes from lambda divided by 1 over n. That's nice and all, but it's not our pivotal quantity. It's just a start because the distribution depends on the unknown parameter. Furthermore, it is not a chi-square distribution, but it's not that far off. Remember, we define a chi-squared distribution with n degrees of freedom as a gamma distribution with parameters n over 2 and 1/2. So I can write this n like this. My X bar has a gamma distribution with parameters 2n over 2 and n lambda. So it's like I'm kind of setting up for maybe a chi-squared 2n because I have a 2n here in place of n. But we don't get that chi-squared until we have a 1/2 as our second parameter. And we know how to do this. We've done this today. if I multiply by a constant, it ends up under the second parameter. I want that second parameter to be 1/2. So you can go for that directly. I think I'm going to think about this in 2 steps though. If I multiply by n lambda, it ends up going under the second parameter. And so we'll be getting a gamma distribution with parameters 2n over 2 and 1. This is not exactly what we want. We want a 1/2 in there. Let me get another color here. I don't know if this is distinct enough, but I'm also going to multiply by 2. So that ends up down there. So we get a 1/2. In other words, 2n lambda x bar has a gamma distribution with parameters 2n over 2 and 1/2, and that is a chi-squared distribution with parameters 2n. So we have a pivotal quantity. It has a distribution that does not involve the unknown parameter lambda, and for this particular problem, we wanted to specifically get to a chi-squared distribution. So we went a little further than just not having it depend on lambda. We pushed it more to get it to a chi-squared. We're ready for step 3. We're going to find critical values. A chi-squared distribution, depending on the degrees of freedom, probably looks something like this. It definitely doesn't, like if we're talking about a chi-squared 1, that is gamma 1/2 1/2. And if alpha equals 1/2 for the gamma distribution, where the PDF has it x to the alpha minus 1, we're going to get x to a negative power, and we're going to get like an asymptote approaching the y-axis. I really don't care. I'm just trying to draw a PDF. In our case, we're not going to have our alpha less than 1 because our alpha is 2n and n is a sample size. It's going to be at least 1. So we're going to get something like this, but it's going to move around. The shape's going to change as n changes. Still, just draw a kind of generic looking PDF. No one cares if you can actually draw this PDF because it's just sitting here for us to imagine putting area 1 minus alpha somewhere. We could put it in the middle, putting 1 minus alpha here, alpha over 2 here, and alpha over 2 here. We can put it kind of in the middle, but off center by putting like 1/4 alpha on one side and 3/4 alpha on the other side. We could start from 0 and go up to something that gives us area 1 minus alpha there and alpha there. And we can even start at something and go up to infinity so that we get 1 minus alpha here and alpha here. I may have scared you off of intervals like this because who wants an infinitely long confidence interval? But in the step 4, when we want to solve down for the unknown parameter in the inequalities, things could actually flip. So if you put a 0 in there and you have to flip things, that's going to turn into like, 1 over something really, really small. It's going to be like infinity. So sometimes starting with this gives you an infinitely long confidence interval, which is technically fine unless anyone asks you to actually optimize what's going on. It's not as obvious just looking at these pictures what is going to be smallest. It depends on how much area is over by the y-axis. I am not going to try to optimize anything here. I'm just going to pick one. I think the natural choice would be this because starting with 0 seems nice. But I'm going to do this one, and I'm just choosing to do this one. You can do any of these. So we want to find the critical values. I didn't write that for step 3, but that's what we're doing. And for the gamma distribution, you cannot integrate this. Yeah, you cannot integrate this even with integration by parts and get a nice answer. So we're doing this one symbolically. So what is this critical value? We're going to use the same notation we've been using all along. For the normal distribution or z-curve, we used z sub alpha to denote a number on the x-axis that captures area alpha under the PDF and to the right. We used t sub alpha comma n to be the same thing for a t distribution, but there isn't just one t distribution. It depends on n, so we needed more notation there. And for what I'm going to do today, I'm going to put a chi-squared symbol and an alpha and an n to represent the number that cuts off area alpha to the right under the chi-squared n PDF. All of these might be the opposite if you see them out in the real world. You might see this t looking like this also, and the chi-squared. And sometimes people, when they say z sub alpha, t sub alpha, any of these, they actually mean area to the left. So be careful. But I'm going to stay consistent throughout this course, and my subscripts are going to denote areas to the right. So now we have notation for the chi-squared. Let's get our critical values over here. This is chi-squared sub alpha over 2. It's a number that cuts off area alpha over 2 to the right. And then we need something denoting its degrees of freedom. For this problem, that is 2n. One of the reasons I chose to go with this picture where I put the area in the middle was just to make sure you didn't fall into the beginner trap of saying this is the negative of that, because it's not. This PDF only lives on positive values. It's not around 0 and it's not symmetric. So using the same notation, if I have area alpha over 2 to the left, then I have 1 minus alpha over 2 to the right. So this number is going to be called chi-squared sub 1 minus alpha over 2, comma 2n. Step 4. Step 4 is going to be to put the pivotal quantity, getting sloppier and sloppier, in between the critical values and solve for the unknown lambda in the middle. Like we want to capture it in this inequality between two values. Let's let W be a chi-squared 2n. I know I've already used this letter before, but it was always kind of in this intermediate step. So this is a new W. If I want to get area 1 minus alpha or probability 1 minus alpha, I could put W between the two critical values we just wrote down, the chi-squared sub 1 minus alpha over 2, comma 2n, less than W, less than chi-squared sub alpha over 2, comma 2n. What in this problem has a chi-squared 2n? It is 2n lambda x bar. So let's put that in there. The final step is going to be to start moving things around so that we isolate lambda in the middle. It's right there. It's pretty easy to get at. Clearly, we need to divide by 2n x bar, and I'm going to do that. And when you do this step, make sure you're not dividing by a negative. It's okay if you do, but inequalities will flip. But n is a sample size that is, 1 or greater, and x bar is the average from an exponential distribution, which only takes on positive values. So everything's nice and positive, and we're going to get chi-squared 1 minus alpha over 2, 2n divided by 2n x bar, and then something similar on the right. So the answer, A, not the, 100 times 1 minus alpha percent confidence interval for lambda for the exponential distribution n based on x bar, all of that is leading to this answer, is the interval chi-squared sub 1 minus alpha over 2, 2n divided by 2n x bar up to the other one, chi-squared alpha over 2, 2n over 2n x bar. So we have what we wanted, a confidence interval for lambda for the exponential distribution based on x bar and in terms of chi-squared critical values. I did say I wanted to compare this to our other confidence interval for lambda in our previous example that was based on the minimum, but I think I'm not going to do that because everything is symbolic, so it's not going to be so easy. And my first one, I tried to optimize the length, and the second one, I didn't even try. But what would be better? They both have the same probability of correctly capturing lambda, and it would be better if you returned a shorter interval. Can't always do this, but keep it in the back of your mind in case you come across a day when you have to provide a confidence interval to someone and you can find a shortest or shorter interval. As a third example, I want to go back to the normal distribution, but not the mean. Suppose I have x1 through xn, iid, from the normal distribution with mean mu and variance sigma squared. I'm assuming the parameters are unknown, and I want to derive a 100 times 1 minus alpha percent confidence interval for sigma squared. I won't even say what it's based on because I think you know what I'm going to choose. So step 1 is to choose a statistic. You should think in terms of estimators for sigma squared, but anything can be an estimator, even a crazy statistic. So yeah, I'm going to do what I think is the common sense approach here and use the sample variance s squared. And every time we use the sample variance in this class, it is going to be the unbiased version. Why did I choose this outside of it being the most natural estimator for sigma squared, or maybe the second most? Maybe it's more natural to divide by n, but we saw that that was biased, is because in the very last class, we looked for a normal distribution at the distribution of the sample variance, or more specifically, so let's head into step 2, where I want to find a pivotal quantity, which is a function of, in this case, s squared and sigma squared, whose distribution is known to us and not depending on any unknown parameters. We just saw in the last class that if you start with normals, the distribution of n minus 1 times the sample variance over the true variance has a chi-squared distribution with n minus 1 degrees of freedom. And that just depends on the sample size, which we are assuming is known. It doesn't depend on the unknown sigma squared. So there is your statistic, and there's the thing you're trying to estimate. And overall, there is your pivotal quantity. This means we want to put this pivotal quantity between two chi-squared critical values. We don't have closed form expression for those, so this answer is again going to be symbolic. But imagine a chi-squared n minus 1. Maybe this time I'll just go from 0 up to some number. If I want area 1 minus alpha versus alpha, then this number here is called, in our new notation, chi-squared sub alpha comma n minus 1. And so if I, I don't know why I keep doing this. I don't really have to do this line, but if I let W have a chi-squared n minus 1 distribution, then we do know that I will get W to be, with probability 1 minus alpha, in between the numbers 0 and this chi-squared critical value. And there are many other ways for us to put that area in. So what in our problem has this chi-squared n minus 1 distribution? It is n minus 1 s squared over sigma squared. So the final step is to move things around and solve for sigma squared in the middle. It's in the denominator, so I want to start by flipping things. And if 2 is less than 3 is less than 4, and you flip things, then you actually have to flip the inequalities. It's going to end up going the other way. So when you flip 0, just think of it as flipping a infinitesimally small number. It's blowing up, and you're going to get infinity. When you flip the middle, you're going to get sigma squared over n minus 1 s squared. And when you flip this other side, you're going to get 1 over this chi-squared critical value. Now, if I multiply across by this, which is non-negative, we will have isolated sigma squared in the middle. While I'm doing this, I'm going to write the inequality in the other direction. So we end up with n minus 1 s squared over chi-squared sub alpha comma n minus 1 less than sigma squared less than infinity. So we've done it, but we did end up with one of those infinite length confidence intervals. A 100 times 1 minus alpha percent confidence interval for sigma squared for the normal distribution and based on the sample variance S squared, because all of that is relevant here, and it's only n, not the, is n minus 1 times S squared over this chi-squared critical value, alpha n minus 1, to infinity. If you're doing your math stat homework or a math stat exam, I would just stop, move on. If you are trying to consult with people later in your life and derive confidence intervals for them, I probably wouldn't want to give them an infinitely long confidence interval. You see where that came from. It came from flipping over 0. So I would go back to this picture and probably do it the other way, where I put 1 minus alpha up here and alpha here. So I go from something to infinity at the beginning, but then that flips. But we are done. Choosing the statistic could be difficult, and finding a pivotal quantity whose distribution is known to us could be difficult. The more math stat we do this semester, the easier that's going to be. And other than that, confidence intervals are pretty plug and chug. Let's look now at a couple of 2 sample confidence intervals for different things. In my first example, here is the setup. I have a random sample of size n1 from a normal distribution with mean mu1 and variance sigma 1 squared. I could write this if I want as like x1 out through xn1, but for my second sample, I'd have to use a different letter, or I could use double subscripts. But it turns out I really don't need to write these out explicitly, so I'm not going to write anything. I'm just going to say I have a random sample of size n1 from this distribution. And then suppose we have a random sample of size n2 from another normal distribution with its own mean and its own variance. So that's what we have as part of the setup. And suppose the samples are independent of each other. Not only is there IID stuff going on within a sample, but between the two samples. Let's derive a 100 times 1 minus alpha percent confidence interval for the difference between the means, mu1 minus mu2. We don't know anything about hypothesis testing yet, but in hypothesis testing, we're going to propose things like, I propose that mu1 is less than mu2. Let's test whether that's true or the opposite is true. It's going to be equivalent to what we're doing here. Because if we find a confidence interval for this and someone actually goes out and gets the data and gives you numerical values, suppose for this, we get a confidence interval of negative 1.4 up to 7.2. This is, has a definition, but it's supposed to be representing an interval of plausible values for this difference. And if 0 is in the interval, as it is here, then we're saying that 0 is a plausible value based on what we're seeing in the data that produce these numbers. This is going to be equivalent to doing a hypothesis test, where we test whether or not mu1 equals mu2, or mu1 is not equal to mu2 or greater than mu2. If you don't know what I'm talking about, alluding to hypothesis testing, just ignore what I said. We'll hit it when we hit it. But yeah, confidence intervals can be hypothesis tests. Is mu1 equal to mu2? Well, I don't know. Did 0 fall in the interval? If it did, you still don't know that, but your sample suggests that. So you have some evidence for it. You haven't proven anything. How do we do this? It's another confidence interval. Step 1 is to choose a statistic or an estimator for mu1 minus mu2. And the natural thing to do here is to look at x1 bar minus x2 bar. And I could write out like where x1 bar, but I think I'll just put some arrows here. So this is the sample mean for the first of the two distributions we're talking about. So it's like a 1 over n1 and then times a sum up to n1. I just didn't really set up notation to write these out. And x2 bar is the other sample mean. That seems like a good way to deal with trying to figure things out for mu1 minus mu2, including a confidence interval. So let's try it. If we can't do step 2, we're going to have to back up and choose a new statistic here. We need to find a pivotal quantity. The kind of sub-step, the beginning of step 2, would be to look at the distribution of this statistic. We know that x1 bar has a normal distribution because a linear combination of normals is normal, not because of the central limit theorem. So this is normal with mean mu1 and variance sigma 1 squared over n1. We have that x2 bar has a normal distribution with mean mu2 and variance sigma 2 squared over n2. I didn't put this in the setup of the problem, but I'm going to go back and do it now. Let's assume that sigma 1 squared and sigma 2 squared are known. We're trying to sort of infer something about the difference in the means. If we knew the means, we wouldn't be doing this problem. If we didn't know the means, I'm not sure why we would know the variance, but it could happen. But really, as we saw in the confidence intervals from last class, it's a stepping stone to replacing them with sample variances. So let's just assume it for now. I want to get an interval for this. I'm using this as my statistic or estimator. So when you put these together, these are independent. I should probably write that first. Because the samples were assumed to be independent. So if we put them together, this is just a simple linear combination of normals and is again normal. If you find the expected value of this and run it across, you're going to end up with mu1 minus mu2. And if you run the variance across, it's been a long time since we've done this, but you're not going to get the variance of one minus the variance of the other. The variance of x1 bar minus x2 bar, we do get to break this apart by independence. We have results about sums, not differences. Let's write, if you just know what it is, then write it down. But I'm going to write this as x1 bar plus -1 times x2 bar. If there was dependence between these two random variables, I need a covariance term. But by independence, this can be written as the variance of x1 bar plus the variance of -1 x2 bar. And then this constant will come out squared. So we end up with the variance of x1 bar plus the variance of x2 bar. Those variances were this and this. So I'm going to continue this line and say that this variance is sigma 1 squared over n1 plus sigma 2 squared over n2. Just don't put a negative in there. It's just not true. A lot of times people just do it. They don't even think it's true, but kind of not even thinking. It's more of that doing statistics while unconscious thing. We have a statistic we're going to work with, and we found the distribution of the statistic, and now we want a pivotal quantity, which is some function of this and the thing we want the confidence interval for, whose distribution is known and unknown parameter free. I think we should go for the standard normal. Let's standardize this. We have this normal random variable. I'm going to subtract its mean, which is mu1 minus mu2, and I'm going to divide by its standard deviation, which is the square root of its variance. So that's going to be the square root of this entire sigma 1 squared over n1 plus sigma 2 squared over n2. This is normal 0, 1. So this is our pivotal quantity because it's a function of the estimator, the unknown parameters, and known things whose distribution is completely known to us and not dependent on any unknown parameters. Let's call it Z. It's a standard normal. Let's call it Z. We are ready for step 3. We're going to do find some critical values. If Z has a standard normal distribution, then to capture area 1 minus alpha, we could put Z between two values that we definitely want the area in the middle for this one, because that will give us a short interval. And I want these guys out here. So the name of this one was Z sub alpha over 2, and the other one is the negative of that. Let me write that down. I'm trying to make them look lowercase, where the one in the middle is a random variable. But you put this entire circle in here. What a horrible arrow on the next line. I don't want to do that. And then so you have this between two critical values and try to solve for this mu1 minus mu2 in the middle. This is going to give you a 100 times 1 minus alpha % confidence interval for mu1 minus mu2 for the normal distributions and the independent samples is given by x1 bar minus x2 bar plus or minus z sub alpha over 2 times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Not only is that a confidence interval, but that is the standard one that you're going to see in a Stat 101 textbook. All of this was based on the fact that this had a normal distribution. And if we don't start with samples from a normal distribution, but we have large samples, we could use the central limit theorem on this. So if we did, and don't worry, I'm not going to write this whole thing again. I'm going to write the setup and then the answer. If we had two independent samples, one of size n1 from the normal mu1 sigma 1 squared distribution, and one of size n2 from the normal mu2 sigma 2 squared distribution, and sigma 1 squared and sigma 2 squared are known or unknown. Maybe we can do these both in one example. You can say if n1 and n2 are large, greater than 30, or I would like them to be even larger, then our x1 bar, the sample mean, is approximately normal by the central limit theorem, with mean mu1 and variance sigma 1 squared over n1 by the central limit theorem. And, similarly, x2 bar is approximately normal. And so the rest of this problem is going to be what we just did. A, or n, approximate 100 times 1 minus alpha % confidence interval for mu1 minus mu2 in this case. So in the case that we have large samples and either unknown distributions or distributions that we can't work with, they're just too complicated for us to get pivotal quantities and critical values. If things are large and you want a confidence interval for this, you could do what we just did and use approximate normality. So an approximate 100 times 1 minus alpha confidence interval for this is again given by x1 bar minus x2 bar plus or minus z alpha over 2 times the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. And we could also have the variances unknown. So if sigma 1 squared and or sigma 2 squared are unknown, we could use the two different sample variances and call it approximately good if we have large samples, because we can justify it by saying that these guys converge in probability to the individual things. And in fact, the grad students on the current homework have to show a little more than that. So I'll talk about this at the beginning next time, but we can show that the square root of s1 squared over n1 plus s2 squared over n2 is converging in probability to the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. So if you want to lend credibility to you using sample variances in place of true variances, informally you'd say they're approximately good because they're good estimators because we have really large samples. But formally, you would say something like this to help justify replacing this with this. Because when the sample's large, you are partway in that journey of convergence. And hopefully you are closer to this side than this side. One more of these normal two sample difference of means example, which is actually going to take us into the next class. We're not going to be able to finish this. I have a random sample of size n1 from the normal distribution with mean mu1, sigma 1 squared over n1, and an independent random sample of size n2 from the other normal distribution. And I want a 100 times 1 minus alpha % confidence interval for mu1 minus mu2 when sigma 1 squared and or sigma 2 squared are unknown. Now we just said, we'll use the sample variances, but if the sample sizes are small, this is not a good idea because we don't have that convergence yet. So I'm going to do what you need to do for a small sample. We've seen this sort of thing before. What I'm going to do does not actually depend on the sample being small, and people probably won't bother doing it with large samples. They'll probably give the previous confidence interval and say, that's approximately fine. But we can come up with an exact confidence interval here. If I replace the sigma squareds by the f squareds involving the t distribution, just like we did when we had one sample. It's slightly more complicated, but this is the fun part. This is, I don't know, most fun part of what we've done today. This can be a hard problem. So today, and I'm not even sure we'll finish case one, I do want to talk about case one. If we can assume that sigma 1 squared equals sigma 2 squared versus case 2 where we can't assume that. You might think that's kind of strange because I'm trying to figure out a confidence interval for the difference between mu1 and mu2, so clearly I don't know what they are or I wouldn't be doing any of this. So how would I know that the variances are the same? I've got three answers for you. I don't know if you're going to consider them answers. One, it's just a building block. Just suppose you know it. Two, we can do a hypothesis test later in the course when we know what that is to try to figure out whether or not this is true and then go forward with what we're about to do here. Three, we can make some kind of argument about our actual problem at hand. Like maybe we sell cereal and we are getting a new box that goes with the new Batman movie or something, so a special edition box. And maybe we have some kind of historical data about how people want the Batman box and we sell more of it, but historically it is known to us already that it's not really going to have a different variance. Maybe something like that could be a case for this. So the easiest thing to just say at this point is it's a building block. It's a building block. We keep loosening up our restrictions. I don't know the sigma squareds and I need to approximate them, but there's really only one thing that needs to be approximated because these are both the same thing. So I am going to start up by calling the common value just sigma squared. So sigma squared is sigma 1 squared is sigma 2 squared. I am going to try to estimate this with a sample variance, but I have two samples. You don't just want to throw them in one big pile and take the sample because they have different means, and that sample variance is a measure spread about a mean and a different mean. Uh, Keep them separate and compute two sample variances. So I'm going to let S1 squared and S2 squared be the two sample variances. I've been avoiding rigorous notation in this all along, but like your S1 squared might be the sum as I goes from 1 to n1 of x1I minus x1 bar squared over n1 minus 1, and S2 squared something similar. I want to combine these to get an estimator for the common variance. One possibility would be to average them. Make this a question. I don't think this is a good idea for a couple of reasons. One, it weights them equally. And what if one sample was really, really much larger, or even just a little bit larger? If one sample is larger than the other, its estimator for the variance is going to be better, and we should give it more weight, I think. Another reason you might not want to use this is when you get to like your step 2 and step 3, I think you're not going to be able to figure out the distributions you need. So maybe we want to use a weighted average like n1 s1 squared plus n2 s2 squared over n1 plus n2. And this will like lean you towards the variance, the sample variance for the larger sample, if there is a larger sample. This makes a lot more sense in that respect, but its distribution is complicated. Instead, I'm going to go with a third option. I'm going to use a different kind of weighted average. I'm going to have notation for it. We're going to call it SP squared. This stands for pooled variance. And like the example that's at the top of the screen right now in the center, it is going to be a weighted average, but slightly different. So I'm going to take n1 minus 1, s1 squared, plus n2 minus 1, s2 squared, over the sum of those coefficients. When you add them together, you get n1 plus n2 minus 2. I am out of time, but we're going to see next time that when properly multiplied and divided by things, we get a chi-squared distribution with a certain number of degrees of freedom, and we're going to make a t-distribution. And it's going to be a lot of fun. So I hope to see you next time on mathematical statistics.